Okay. You're able to see it from here. Just a minute. Right. So did we see this fundamental theorem of arithmetic? I'm sure that you would have learned all these things, right? So what does this chapter comprise of? Actually, if you see, it's a very, very, very small chapter, right? So what do we actually study? We discussed in the previous class. So you need the basics of number systems, right? So we already discussed what are the kinds of numbers or what are the types of numbers we are going to deal with, right? You guys remember all those things, right? So what were the types of numbers? We saw what are natural numbers, whole numbers, integers, then rational numbers. Under rational numbers, you had two categories: rational numbers which terminate and rational numbers which do not terminate. Did we discuss this or not? Yeah. So is there any doubt that you have? So you know what is the rational number, right? What is it?
Rational number is any number that can be expressed in the form of p by q, where p and q are integers and q is not equal to 0.
Yes, p and q are integers and q is not equal to 0. And generally, when you try to represent a rational number, what you do? You try to represent it in the form of simplest form, right? So, if, for example, I have common factor between the numerator and denominator, you will always try to stop it with the simplest form, right? What do you call when it is in the simplest form? What do you call the numbers in the numerator and denominator as?
Co-primes?
Yes, they are called co-primes. So, what do you mean by co-primes? Those numbers which do not have highest common factor other than 1 are called as co-primes. So that is what you're supposed to do. Based on, so why am I speaking about co-primes? Where do we use this concept? Let me see how much you have worked on NCERT. Proving that the given numbers are irrational numbers. At the time, we use the concept of co-primes, right? So to what I remember, last class we started with fundamental theorem of arithmetic, right? So we started with this. I hope you guys are able to see. You are able to see? Yeah. So fundamental theorem of arithmetic, what does it state? So this is a statement taken from your MKG book. So what does it state? You talk about a composite number. Every composite number. What do you mean by a composite number? Exactly an opposite of what is composite number? It is exactly an opposite of prime number. So when you talk about composite number, you have factors other than 1 and itself. So when you do that, will you be able to represent them in terms of prime numbers is what the question is. So when you talk about fundamental theorem of arithmetic, it mainly speaks about a composite number being expressed as a product of prime numbers, right? So prime numbers, and how can you do that? Using the prime factorization method. So every composite number can be expressed as a product of whom primes, and this factorization is unique. This is a very important term you need to have in your mind. This factorization is unique. Okay. Apart from the order in which the prime factors occur, what is the meaning of this? Last class you asked me, remember? So apart from the order in which the prime numbers occur means, what is it? It can at any order. It is not necessary that you have to start with a smaller number and then go to a bigger number. You can start with anything you want, but at the end of the day, what will you do? You will write it as product of those numbers raised to the power how many ever times those numbers are come. Right? Do we do this? Yes. Next is, why do we even need to go with the prime factorization method? Next question to be answered. Why do we need it? Every time I put this question, why? What is the advantage or what is the use of it? How is it saving our time? Division is okay, one thing. Again, in the case of factors and multiples only, right? So when you want to, when I give you two numbers, you can find the highest common factor between those two numbers using one of the algorithms. What is it? Euclid's division lemma. You know how to do it, right? I hope there is no doubt in that, right? Now the next question is, how will you find the same HCF and LCM using prime factorization method? That is where the fundamental theorem of arithmetic is going to help us. Okay. So last class we discussed about two numbers. What were the two numbers for which we found the HCF? The previous class. I gave it from the textbook only, right? So what were the two numbers for which? $725. 7 to 721 and 5595, correct? Okay. Now I ask you to write the numbers in the so there is a composite number 721 and 595 are composite numbers, no doubt in that, right? So if I ask you to do prime factorization and write it as product of primes, can you guys do that? Do for both the numbers individually and tell me. For 721, where will you start with? We'll start with 3. Will it work? 3 worked. You saw the 21 and you got tempted, right?
Yeah, I
7 is there, no, you don't have the remainder 0 there. So try something else. So 1 means what other number can you try?
7 will come.
So try it out. 7 will come. 7 comes, right? 7 into 13. So 721, you can write it as 7 into 13. What about 595? Obviously, you can start with 5. 5 into, I'm not checking it. I hope everybody got this. Most importantly, what are you supposed to do when you're doing this prime factorization? You need to express a composite number in terms of only primes. Okay. So when you do this, observe. So 7 power 1, 13 power 1, 5 power 1, 7 power 1, and 17 power 1. Now, if I ask you to write something in this form and ask you a question of what is the HCF, will you be able to tell me what is the answer? You'll check for the number which is common in both and the highest number. So obviously it is going to be 7. Is that not what we got when we use Euclid's division algorithm? Right? So this fundamental theorem of arithmetic will also help us in another context. What is it? To find the highest common factor, and at the same time it will help us to find the LCM also. How is it going to do? Okay, so that's what the concept is given here. So HCF and LCM using prime factorization method. So what can we do is in HCF, right? You will find the product of smaller powers of each common prime factor in the factorization. What is the meaning of this? So I want you to underline this from your MTG textbook only again. Say the textbook it is there. Please underline. You can get it done.
My back is too heavy, so
Okay, that's fine. So page number 2. So I want you guys to tell me the meaning of it. What are we trying to say? Product of smallest power of each. Underline that word each. Product of smallest power of each common prime factor in the factorization of the numbers. Think. Don't be in a hurry to tell me. So for example, what am I supposed to do with this problem? The 721 and 529, 595. So you take the common prime number. So if you observe, the first one has prime number 7 and 13. Second has 5, 7, and 19. So what is common in both? Sorry, 17. 5, 7, and 17. So what is common in both? 7. So among 7 also, had there been a scenario where this was 7 power 1 and here you had 7 power 2. Now what is the statement telling you? Smallest power is what you need to take and then you need to multiply them. Right? When you multiply them, what will you get? You will still get the highest common factor between these two numbers. But you know what is the biggest advantage? Here, you need not stop it with 2 numbers. You can do it for 3, 4, 5, any number that are given. Right? So that is how you do find the HCF using the prime factorization. Now the next question is how you find the LCM, least common multiple of both. So here also you take the product of whom? So product of the greatest power of whom? Yes. So here, 1 minute, show your notes. So here also So product of the greatest power of each prime factor involved in the factorization of numbers. Right? Are you able to understand this? right? And most importantly, I'm sure you would have known this fact already. So if you have two numbers, and for those two numbers, you are finding HCF separately and LCM separately. I'm talking about two numbers. You're finding HCF separately and LCM separately, and you can say that the product of HCF of those two numbers and LCM of those two numbers will be what? The product of those two numbers, provided they both are positive integers. So, if you have two positive integers, if you find the highest common factor of those two positive integers and the least common multiple of those two positive integers, the product of these two should be equal to the product of those numbers. Right? Should we try that? Right? Now listen, let's go with a simple case. Let's say you need to find the highest common factor of 24 and 56. Find the HCF and LCM and then we class using this logic. 56. HCF is how much? Highest common factor is. So what are the factors that you got for 24? 24, your 2 power into 3. So 2 power 3 is 8 into 3 is going to be 24. Okay. 56, 2 power 3 into 7. So what is the highest common factor? So it will be 8. And what is going to be the LCM? It will be 8 into 3 into 7. So how much is it? 1? Okay. So 168 into what was highest common factor? 8 should generate what? So 168 into 8 is how much? Do it fast and tell me. 448. How will you get it? 8 ones will be 4 no. 8 8 is 64, 6, 8 6 is 48, 4, 1, 1 3 4 4, right? Now do 56 into 24 and find out. Is it working? So 56, you have 24, 24, 10, 20 plus this 22. So 1 0 2 2 2 4, 4, 4, but I'm getting 1 2 2 4. 20 plus 12. So 20 plus 12 is 32. Sorry. 1 3 4. Yes. Right. So what did we conclude? So you can use the prime factorization, you can find HCF, you can find LCM at the same time. When you have two positive integers, the product of HCF and LCM of those two positive integers equal to the product of those two numbers itself. Now you have an example, problem number 5. Okay. So that is three numbers are there. What are the three numbers? 917, sorry, 917 and 729. Find the LCM and LCM quick without looking at the solution. 9. So in page number 3, this one. 97, 117 and 729. So 9 is written as obviously 3 square is another option. 117.
3 square is 30.
Okay. 729.
3 power 6.
3 power 6. 3 power 6. That's it. So what is going to be the highest common factor? It should be the multiplication of, you take the common number with the least power. So what is the least? So what is the common number among all the three? 3. So 3, and the least power that you are able to see is 2. So 3 square is 9. So 9 is going to be the highest common factor. Then what about LCM? Then what about LCM? So LCM is what? So how did you do? So which number did you multiply?
9477. 9477.
So 9477. Okay, 9477. Now the next task. Multiply 9477 and 900. That is highest common factor of ABC and the least common multiple of ABC. We found it. Right? Now we are going to find the product of them. And what is expected? What is expected? Product of LCM and HCF of these three numbers. So 9477 into 9, how much are you getting? Eight five 85293. Is this what everyone is getting? Okay. Now, what are the three numbers for which we did the we found the HCF? 9 into 117 into 729. What is the answer? 76736. Sorry, 767637. You're able to understand that. What is the important point that we are able to observe from here? So when you take HCF into LCM, it is applicable only for 2 positive integers. It is not applicable for 3 positive integers. Okay, so that is what is given in the competition we to observe. So for 3 positive integers A, B, and C, HCF of ABC into LCM of ABC is not equal to the product of these three numbers. Where ABC are again what? They should be positive integers. Okay. Then what about LCM of ABC? How you write it in terms of HCF of ABC? Please make a note of this formula. So write it down. LCM of ABC is equal to A into B into C. So write down that formula. A into B into C into HCF of ABC. Okay. So A into B into C is the highest common factor of all the three numbers divided by what? HCF of two numbers taken together. So two numbers taken at a time. So you can say HCF of AB, HCF of BC into HCF of CA. It is a cyclic pattern. AB, BC, C. Similarly, if you want the highest common factor of ABC, suppose there is a problem where they have given you the least common multiple of ABC and AB, BC, and CA. Then how will you find the highest common factor from that? HCF of ABC will be equal to. So what is given in the question? Listen to this carefully. What did I say is given in the question? They will give you the LCM of ABC. Okay, they will give you the LCM of AB, LCM of BC, LCM of AC, and they expect you to apply this formula and find out the HCF. Then how is it going to be? It's exactly the same. Only LCM and HCF are swapped. highest power. Can we do this for the previous one? For the three numbers 9, 170 and 729, can we find out the HCF using the LCM? Can we try that? So LCM you already have. What is that number? Okay, or else we can go in the reverse. We'll find LCM using LCM. That is easier. So highest common. So what are we supposed to do? What are the three numbers? 9 into 117 into 729. So that is in the numerator. So what are we trying to find? HCF of 9, 117 and 729. So how are we doing it? A into B into C accepted into, we already got the LCM of those numbers. What is LCM? 9477. The whole divided by, this is what I'm concerned about. Find LCM of AD, BC and AC. Can you do that? For who? For which two? For AB 9 and 170. Because it is divisible. No? 117. So LCM of 9 and 170. What did you say? Yes, because it is C square into 13. So LCM of 9 and 117 is 117. I hope everybody is able to understand. Right? So what is the LCM of 117 and 729? Yes, that's a big number. So let's not let's. That's what the answer 9477. So let's not be in a hurry to multiply. Okay, 9477. We already know this. So LCM of 729 and 9 is how much? 729. That is 3 power 6. Now can you substitute everything and check if you are getting the HCF as 3 square? See if this working. Is there anyone having doubt with this? So which one is confusing? So did you understand why I did this? Did you understand why I found the LCM for 9 and 170? You understood, no? For me to update this formula. So LCM of 9 and 117 means what are we supposed to do? Take the common number with the highest degree. So common number in both 9 and 117 is 3. What is the highest power of 3 in both the cases? Among both the cases? 2 only. So 3 power 2 into the other number, that is 13. So you read the statement. What does it tell? Product of the greatest power of each prime factor involved in the factorization. So of each prime factor. So 3 square into 13 is another prime factor involved in these. So that is why it is 13. So 3 square into 13 is going to be 107. You understand? Similarly, LCM of 117 and 729. You tell me of 117 and 729. 3 is common. Yeah. Summon 3, which is the highest power? 3 power 6. So 3 power 6 into what is the other prime number, which is 13. So 3 power 6 into 13 is what is this? 947. Okay. LCM of 729 and 9. What is common among both? 3. So 3, what is the highest power? So 3 power 6 is 729. You understood? Yeah. Substitute it. Is there anyone else who is having doubt? Did anyone get the answer as 9? So see if you're this will help you to understand and cancel common terms. This is mainly problem based on exponents, not multiplication skills. Okay. So what are we trying to find? HCF of 9, 117 and 729. What is it? A into B into C into, yes, 3 power 6 into 13. That is what the LCM is, divided by LCM of A and B, that is 117 into LCM. So 3 power 6 into 13. This is LCM of BC into LCM of CA is 3 power 6. See, beautifully they will get cancelled. 117, 117, gone, 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 gone. So it will be left out with 9. Right? So this is how it works. So this formula is right. We have verified it, right? Similarly, you can do it for other problems as a part of homework. Concept is clear, right? So what is the next concept we are supposed to discuss? So what is there in the textbook? So we need to speak about irrational numbers. So what are irrational numbers? Numbers which are, see, one way of differentiating between rational and irrational is numbers which we cannot write into the form P by Q, where P and Q are integers and Q is not equal to 0 are called as irrational numbers. That's it. Okay, is that the only way of defining it? Yeah, non-terminating and non-recurring. This gives me another important question in my mind. You mean to say rational numbers are always terminating? They can be repeating. So how are rational numbers classified as? They can either be terminating or they can be non-terminating, but at the same time, what will they tend to do? They will repeat them. So the numbers will keep getting repeated. Is that right? So then you can call that as a rational number. Okay. So what does this theorem has to tell us? So what is the theorem telling us? Theorem 1. So I want you guys to tell me the meaning. You have the same thing in NCERT as well. What is it? And where do we use this concept again? That a given number is irrational. So you use this concept, right? Because generally every problem, how will you prove that a given number is irrational? Only by using, can we directly prove it? Can we directly say that this number is irrational? We can say, provided if you can take the square root of 3, show what is the big number you have, you can say it is a non-terminating and a non-repeating, so it's a irrational number. But with respect to your syllabus, you have a pattern which you need to present. So we go with the method of contradiction. So first, what do we assume? We assume it to be a rational number. Are you guys able to connect with what I'm trying to say? You have done this, right? Okay. So you will assume that root 2 is equal to A by B, where A and B are co-primes, right? Then what you do? You write A is equal to. You will follow certain steps. What are the steps? Can someone tell me? For example, if I ask you to prove root 2 is an irrational number, what will you do? You will first write root 2 is equal to. You will assume it to be rational first, where A and B are co-primes, right? Then you will write A is equal to root 2B. Then what will you do? A is equal to 2B square. Then what will you say?
So, A is a number divisible by 2.
Okay.
A is also
Sorry, A square is a number which is divisible by 2. Then you will
so
say
A is a number
A
divisible
is a
by
number which is divisible by 2. Then you cannot say A and B are co-primes. That's what you say. So, but where did you take that idea from?
If the number is square, then the square will have pairs of factors. So
Yeah.
if I know one factor, which is a prime number, I know that it is there in both the.
Can you give me an example? And maybe to
Like,
understand. You can say that.
yeah. So if it is 144. So I know that it's 12 into 12. So if I just know that it's 144, and if I know that 144 is equal to 3, let's say 2b something. So if 144 is equal to 2b, so I know that 144
Is divisible by 2.
is divisible by 2, and
144 is 12 square.
root 144 also will be
It's
divisible by
also
2.
divisible by 2. So that's what this theorem has to tell us. Now read that statement. Okay, you took an example to explain. But when it comes to mathematics, we need to go with some general terms to prove it, right? Right? What is the statement telling? I want you people to give me an explanation of what they are. So read it and tell me. So what are they trying to say? If a prime number P divides A square, if a prime number P divides A square, then P divides A, where A is a positive integer. So there is a prime number. Okay, that prime number is dividing whom? A square. Then you are saying that the same prime number will divide A also, where A is a positive number. But how will you prove it? What are the steps that we can follow to prove it? I'll give you a minute time. Okay, just go through the. Let me know if you have. So here, I'll just give you one thing. Okay, whenever you're reading the theorem, right? So I'm just building self-study process. I can teach you, that's a reference to me, but I want you to think. That is the reason I'm asking. So when you take a theorem, right, in this theorem you say there is an if and a condition that is given. So the statement itself starts something like this: if there is a prime number p, okay, if I have a prime number p in my hand which is able to divide a square, then I can conclude something. What am I concluding?
That divides by its A square.
P divides A also, where A is some positive integer. Means what I'm trying to say is, if something of this scenario can happen, then I'm trying to say this also will happen. So this should happen. And I'm putting a must condition. Are you able to understand? So based on this only, we need to start our. So where will you start the? If at all you make this kind of a statement, like she gave me an example of 144. If I make it saying that I want it to be proved in a generic manner, how will you do it? So you need to start with the condition which you are saying should be true. Right? Then you do the reverse analysis. So first step, what they do is look at the way the proof is structured. Okay. Let prime factorization of AB. So the number A which is there, from the fundamental theorem of arithmetic, we know it can be written in terms of other prime numbers. If I take A as a composite number, so A will be equal to P1, P2, so on till Pn. What are those numbers called as? They are called primes, prime numbers, right? So how many numbers are there according to this one? We are saying that that A can be divided into n prime numbers. That n can be 1, 2, 3, anything, we don't know, but it is a generic proof. Okay, when that is a scenario, then if you square on both the sides, what will happen? A square will be equal to P1 into P2 into so on till Pn, the whole square. So how can you write a square in terms of multiplication? Square is basically a number multiplied with itself, right? So when you write it like this, P1 square, P2 square, so on till Pn square. Now what is the condition that is already given? If P divides A square, means that is already given, that is done. You need not prove anything that P is going to divide A square. It is already dividing. If that is the case, now if P divides A square, what can we say? What can we conclude from that kind of a statement? So if P divides A square, can I say P is also one of the factors of this? Guys, are you able to understand what I'm saying? Do you know the proof for this, by the way? Did you learn the proof? No, right? So I'm just making you think. Proof is for this one, I'm repeating, it's not very important from your exam perspective, but it definitely improve your thought process. You will understand how you're supposed to read a theorem. That is what I see many people mistake. Okay. So I'll start it again. So what did we say? We are trying to prove that P is a factor of A. Okay. So let the prime factorization of A be P1, P2, and so on till. So can you please write it down? Yeah. Write it step by step. So what is the first step we are saying? So can you please write down the statement also? So here I am write down the statement. So whatever statement is given there, please write it down. If a prime number P divides A square, the prime number P divides A square, then P divides A. So P divides A, put that A with an inverted comma. So highlight it. Okay, where A is what? Where A is positive integer. Please underline that. All these theorems, you need to understand what kind of numbers we are dealing with, natural numbers. So when I say positive integers, can I call them as natural numbers also? Okay, so what is the first step of the proof we are going to start with? Let A be written. So A is the number for which we are trying to prove that P is a factor. So I am saying I'll start with A. So I'm going to take the idea from the fundamental theorem of arithmetic stating that any number can be written as product of its prime. So start the proof. So first let A be equal to, let A be equal to, that is A equal to, what is it? P1 into P2 into so on till Pn. Where P1, P2, so on till Pn are primes. Okay, I hope this step is clear. But what is already given? P divides A, we have to prove. They only told P divides A square. So we have to square and then incorporate this P. So you have considered let it is, whenever you write let, it is something which we are considering. It is not given. Okay. Next step is what? Which implies on squaring A, I get A square is equal to P1 into P2 into so on till Pn, the whole square. Right? Are you able to understand this? Yes. So which can be written as, so A1 into A2 into so on till An square can be written as A1 square, B1 square. So you can write the square of individual terms. Are you able to see from there, or is it very small? It's fine. So you can write it as P1 square into P2 square into so on till Pn square. Please write down. Now what is given? So write down the next step. It is given that P divides A square. Okay, it is given that P divides A square. So what can you say? From where we can conclude that P is a factor of, P1 square, factor of P1 square into P2 square, so on till Pn square. Okay. Now comes another important term. Read this, the fundamental theorem of arithmetic. Please read the statement again. Read the statement. So P is a factor of, so did you guys understand the previous step that I wrote? P is a factor of P1 square into P2 square into so on to Pn square. Now what is the fundamental theorem of arithmetic state? Read it carefully. Every composite number, please read it. Every composite number can be written as a product of its primes. What is the important word? Underline. So what do you mean by the unique? So when you write it as 2 square. You will not write it as 2 square into 2. Are you able to understand what I'm trying to say? So that is the meaning of unique. So each number will be unique raised to some power. I mean, does it make sense? Are you able to understand what I'm trying to say? So, what is the previous step that you told? P is a factor of P1 square into P2 square, so on till Pn square. So, how many factors did we try to write A square? Oh, sorry, AS. N factors. So, when P is also a member of this batch, then P should take any one of the values from 1 to N. That is the meaning of unique. So, I'll write this thing on the board. I know it is slightly tough, but think about it. What I'm trying to say is A is equal to P1 into P2 so on till Pn. N primes are written. So A square you have P1 square, so P2 square into so on till Pn square. You know that you can write it in dots also, right? Yeah. a part of this gang. So P should be a part of this gang. But what did we do into the first step itself? We told A is a product of only n primes. So if this is not a part of this gang, then how many primes should have existed? You're able to understand, if I call this as a separate number apart from these n numbers, then how many factors should A square add? Should have had n plus 1. But what is fundamental theorem of arithmetic stating that every factor is unique? So what should happen is this P should either be P1, P2 or whatever. So when that will be the case, since it is already a part of this, we can conclude that this divides this. Okay, so actually we are doing the reverse process. As I mentioned, I know the stuff I can understand from your faces, but try once. Okay. So this is only the first step. Maybe 1 month or something down the line, you will be able to understand what you will be able to practice. But I can make an attempt. Okay. So that is what I'm expecting. So you can first write on the proof. But at least now you concentrate on one more important term, right? That was unique at least. At least know something has gone into your brain. Right? Next time when you're reading, concentrate on these steps. Okay. So what is given? We know that so if you look at the statement in page number, if you look at the first line of page number 4, what did they tell us? Read it carefully. So we know that the primes in the factorization are unique there. So where did we derive it from? Fundamental theorem of arithmetic. That's where the statement came from. So we are trying to connect the dots.
Can we also say that the square of a number can never be a prime, and P is a prime number?
That also is.
So it must be a part of the first one.
You can say that. You can say that. But we are taking the help from we are trying to move from this year's syllabus, right? To prime factorization from the fundamental theorem of arithmetic. Okay. So what are they saying? We know that primes in the factorization of P1 square into P2 square and so on till Pn square are unique. So where is it? It is coming from the fundamental theorem of arithmetic. So P is a prime which is one of the primes of what? Of this gang. P1, P2 or so on. So it should have been any one of the numbers. So if it is a part of this gang, then what will it do? It will divide A. So when it is a factor, so when P is a factor of A, can I say A is a multiple of P? I told you the first class. P is a factor of A, then A is a multiple of P. When that is the scenario, the statement that they gave is 100%. Okay, that is the proof. Okay. If you understood, if not, don't worry too much. You'll slowly understand. Okay. Now, having this kind of maturity, try to answer the question of proving that 7 is division. So you have an illustration, right? So what is the illustration? So show that root 7 is division. Please do the steps and show it to me. So you're using the contradiction, right? So first we will assume that root 7 is a rational number. Is there anyone who needs help? You can do it. So write with clear steps. Okay.
5.
A square is equal to 7B square. A is a multiple of 7, so A is equal to 7. Again, 9 are looking simple. Right? Is there anyone who needs help? Just go to the other player. So I just give you the final steps that we're supposed to follow. See, there is only one method, right, in which we can approach. Follow this method alone, that's not. So what are you going to do? First, you will assume that the given relation number is a by b, where a and b do not have any common factor other than 1. So next step is what? A will be equal to root 7b. So what will you do on the next step? A square will be equal to 7b square. So what can we conclude from this? 7 divides a square, which implies 7 divides a also, except. Okay, let me call this as equation number 1. Since 7 is a factor of a, since 7 is a factor of a, according to this, that's what I understood. Can I write that a is equal to 7 into some other number c? Can I write it like this? Right. Then what will I say? A square will be equal to 49 times c square. So a is equal to 7c means what can I say? C is a factor of a. This would be in your mind. Is there any confusion here? Is every step clear? Okay. So a square is equal to 49c square. But from 1, we know the fact that a square is 7b square. Okay, take this and substitute. So when a square from 1, this is what you are getting. So using this in 2. So using this in 2, what can I say? 7b square will be equal to 49c square. This and this will get cancelled. So I can say b square is equal to 7c square. So from this, what can I conclude? 7 divides b square. So 7 also divides b. So 7 is dividing a and 7 is dividing b. So what did we assume to the first step? We assume a and b are co-primes, but our assumption is getting contradicted. Hence, they both are. Hence, its number is division. So these are the steps that you need to do. Just follow these steps at enough. Okay. But did you get clarity over the theorem? Okay. So shall we see the theorem number 2? There are only 2 more theorems. With that, we are done with this chapter. Okay. So what is theorem number 2? But before that, I want to explain about the rational numbers and their decimal expansions, which would have learned at last year. Did you? Right, you know, so there are 2 things. One is they'll give you a rational number using long division method, you have to convert it into the decimal form, or they'll give you the decimal form, then using some assumption, you have, so using some multiplication factor, you need to convert it to the form p by q. You guys remember this? Yes. So in that also you have 2 scenarios. What is it? One is terminating, and the second is non-terminating and repeating scenario. Okay. Now, so we know that decimal expansion of rational numbers p by q are either terminating or non-terminating and repeating themselves. Okay. Let us consider some terminating decimal expansions. For example, if I have 0.25, how will I write it in the p by q form? It's very simple. So how did you get it? What are the steps to be followed? X is equal to 0.25. So it's a terminating value. Count the number of decimals that are there after the point. So you'll add those many number of zeros and you'll write it as 25. So X will be equal to 25 divided by 100. But now we are slightly mature, so you'll directly write it as 25 by 100. Right? So 25 by 100 means, but you should always stop it with the simplest form. So you write it as 1 by 100. Right? So 1 by 4, how can you write it in terms of 2 important numbers that are 2 and 5? Any idea why we are considering only 2 and 5? You would have learned this, right? So if the denominator has 2 and 5, right? When you combine them, you will get a 10. So when you have zeros in the denominator, it is easy for you to tell whether the number is terminating or not terminating. So that is the reason why we only choose these 2 numbers. Okay. So 1 by 4, this is what you have learned last year. But this year, on a slightly higher note, you will try to write the same number in terms of 2 power something into 5 power something. 1 divided by 2 power 2 into 5 power 0. Can I write it? So 1 divided by 2 power is 2 into 5 power 0. Now, does it make sense? Similarly, can you try for 0.773 and tell me? 1 minute time, do it fast. 0.773, the next one. Next one. Because you would have got it as 1000. So when you write 1000 in terms of multiples of 12, what do you have? 2 power n, 5 power n, 5 power n, where n and n both are same. They are the same numbers. 2 power 3 exact is the power for 5 also. Got it as 5 power 3. Right. So how does this help us? If at all there is a scenario where you get a challenge stating that they'll give you a fraction and ask you to find whether this fraction has a terminating value or a non-terminating value, then what logic can we use? We can take the help from the prime factorizations and write the denominator in terms of 2 power m and 5 power n and understand whether it has a terminating value or a non-terminating value. Is that right? Does it make sense in the first place? Right? You understood why we choose 2 and 3? Sorry, 2 and 5? Now see, there is an important point that is given below that 0.773. What did they give? In each case, the terminating decimal expansion reduces to a rational number form. So you're able to write it because it's a terminating decimal value. Obviously, it's a rational number. So you can definitely write it in the form P by Q, where Q is able to get factorized in terms of where P and Q are what? P and Q for sure, you're going to stop with the form of co-primes. So fortunately, 773 and 1000, you didn't have any common factors, so you didn't do anything. So you directly factorize 1000 and try to write it in terms of 2 power something and 5 power something. That is the reason why you got 2 power 3 to 5 power 3. Okay. For example, if you get something by 100, right? 100, how will you write it in terms of 2 and 5? 100 is basically 4 into 25. So 2 square into 5 square. So when you initial step itself, you have co-primes in such a way that the denominator is undisturbed. Then you will write it as 2 power something into 5 power something. For example, let it be 100, let it be 1000 or whatever it is. You will be writing in such a form. For example, 10, 2 power 1 into 5 power 1. 100, 2 power 2 into 5 power 2. 1000, 2 power 3 into 5 power 3. 10,000, 2 power. So the numbers will be the same when the denominator is undisturbed. But in the previous problem, if you see 0.25, we will get it as the powers of 2 and 5 are not same. Why? Because they had common factors. They had common factors. You're able to understand the logic? Right. So where P and Q are co-prime and the prime factorization of Q. So the denominator's prime factorization will decide whether that particular rational number has a terminating or a non-terminating value. Is that clear? So how should the form look like? In each case, of the terminating decimal expansion, when you reduce it to the form P by Q, where Q is not equal to 0, the prime factorization of Q is of the form 2 power m into 5 power n, where m and n are what? Non-negative integers. What do you mean by non-negative integers? They are whole numbers. They are not natural numbers. Okay, because 0 can be included. That's what the first example told us. Right? 5 power 0 we wrote it. So you can write it. Okay. So this is what happens with respect to whom? Terminating decimal values. Am I clear? Right? So based on this, can we have a look at theorem number 2? I want you guys to read and tell me what is the meaning of it. Try to read theorem number 2 in page number 4 and tell me. Let x be a rational number whose decimal expansion terminates. Okay. Then x can be expressed in the form of p by q without a doubt, where p and q are 4 primes, and at the same time the denominator value q can definitely be written in terms of 2 power m into 5 power n. That's what the example tells us. That's it. Right? Where m and n are non-negative integers. Now we are going to speak exactly the reverse of the theorem. I want you to read and tell me what is the difference between theorem 2 and theorem 3. Right? So what did they say? So if you saw this theorem, how are they starting? If something happens, then this will happen. So whatever is there after the then, right, that is what we need to do. That is how theorems work. Okay. So theorem number 3, what are they saying? If a rational number is of the form p by q where q is not equal to 0, and the denominator q can be written in the form of 2 power n into 5 power n, then definitely we can say that the rational number has a terminating value. If not, you cannot express it. Provided m and n are what? Non-negative integers, where of course you can include 0. So clear? So based on this, can we try out some problems? And last theorem is there. Sorry, theorem number 4. What does theorem number 4 tell us? Let x be p by q of x is equal to p by q be a rational number such that the prime factorization is not of the form 2 power m into 5 power n, where m and n are non-negative integers. Then x has a decimal expansion. It definitely has a decimal expansion, but how will the decimal expansion look like? It will be non-terminating for sure, but rational. So in both the cases, we are dealing only with rational numbers. So if you observe in a bigger classification, real numbers are classified as rational and irrational. So we saw how to prove irrational numbers. Last year, you would have seen how to plot an irrational number on a graph sheet, on a number line. Get done with irrational numbers. So this year, what we are doing is we are seeing how to find out whether the given rational number is terminating or not. This is the reason you are learning nothing else. Are you able to understand? So I think this one is 1.4. This one exercise of 1.4, right? From your textbook. Can we do some problems? Without actually performing the long division, state whether the following rational numbers will have a terminating decimal or a non-terminating decimal. Non-terminating and repeating decimal expansion. Suppose you take 31 divided by 625. 31 and 625, are they co-primes or not? Is there co-primes? So 625, how will you write it? 2 power 0 into 5 power 0 into 5 power 125 into 5. 5, 25, 125, 6. So 5 power 4. So it has a terminating decimal value, right? Similarly, 19 divided by 2 square into 5 cube into 7 power 5 without a doubt. Because what is the extra number that you have? You have 7. So using prime factorization, they wrote it in terms of 2, 5, and 7, all the 3 prime numbers. But since 7 is there, it is going to be non-terminating at the same time, repeating itself. Now, the next question is express 0.7373 and so on in the form of p by q. This is actually a 9th step. Remember? Remember? Yeah. Yeah, level 1 assignment it would have been there. So x is equal to 0.73 with a bar on top of it. Can I write it? So you have to look at the number